Let's go over the whole of AQA waves for A-level physics. We're going to start off with the oscillations of the particles in a medium. We need to define a few terms. Let's start off with the amplitude. This is defined as the maximum displacement from the equilibrium position and is illustrated with these blue lines across here in this displacement against distance sketch that I have across here. On to our next definition, which is the frequency. Remember the equation for the frequency, shall we just write this over here as well, is that frequency is defined as 1 over the time period. And as such, it's defined as the number of completed cycles per unit time. Please note that sometimes you're asked to define units. The SI unit for frequency is the hertz. How would we define the hertz itself? Well, that is the number of cycles per second. Remember, if we're defining a unit, we can only define it in terms of other units. We can also define the wavelength, which is the minimum distance between 2 points on a wave that are in phase. For instance, this point over here, let's say point 1 and point 2, they are in phase and the distance between them is known as the wavelength. The speed of a wave, on the other hand, is the distance traveled by the wave per unit time, and the famous equation, the famous wave equation, is that wave speed is equal to frequency multiplied by wavelength. And now let's talk about the phase of a wave. The phase describes the fraction of a cycle covered up to that point, and it can be measured in either degrees or radians. Here's a little example. I just have a displacement against distance. Please note that this could be, for instance, displacement against time as well. The concept is exactly the same. Each point is going to be assigned a value which is a fraction of a completed cycle. Please note that one complete cycle is equivalent to 360 degrees, which is also equivalent to 2 pi radians. Why is that? We're borrowing some mathematics from a circle essentially, because after we complete one cycle we come back to where we started, kind of like if we were moving in a circle and we come back to the point where we started. Each point will be assigned a phase. For instance, this point number 1 over here has a phase of 0 degrees, 0 radians. The next one here is a quarter of a cycle, so point 2, which is 90 degrees, which is pi over 2. This one here, point 3, is going to have a phase of 180 degrees, which is pi radians. Point number 4 will be 270, which is 3 pi over 2 radians. And the last point here, point 5, is going to have a phase of 360 degrees and 2 pi radians. Now, a phase difference describes how far out of sync 2 points on a wave or 2 points on separate waves are in degrees or radians. For instance, the phase difference between, let's take points 3 and 4. So to go from here to here, I just need to go up with 90 degrees, which is also pi over 2 radians. Let's do one more. I don't know, shall we just say points 1 and points 3? Well, the phase difference between them is simply 180 degrees, which can also be expressed as pi radians. Here's an example question on phase difference. So the distance between points 1 and points 2 is shown in the diagram. This here is just 0.5 centimeters. If the wavelength of the wave is 1.2 centimeters, find the phase difference between points 1 and 2. We need to express our answer in radians up to the appropriate number of significant figures. There's a formula that we're going to find very, very useful, and that is that phase difference is going to be equal to the distance between the 2 points on the actual waves, basically this distance here, d, whatever that may be, divided by lambda. This here is going to give us the fraction of the cycle, and then multiply this by 2 pi radians. Please note that if this was in degrees, rather than 2 pi, we would write 360 degrees. But we're going to stick to radians because that's what the question is actually asking us. Our phase difference is the distance between the two waves, which is just 0.50. Divide that by the wavelength, which is given in the question, 1.2. Multiply this by 2 pi. Because the question is asking me to do this in radians up to the appropriate number of significant figures, I'm not going to leave this as a fraction of pi. Putting this into the calculator, we get 2.617199, but all of our answers are up to 2 sig figs, so we're just going to write 2.6 radians. Just a quick little note that I thought would be very useful for you. Well, here are all of the phase difference equations. If we have a displacement against distance graph, they can be given different symbols, but if the distance between 2 points is d, then the phase difference is going to be that distance divided by the wavelength times 360 if we're in degrees. If we're in radians, it's going to be d over the wavelength times 2 pi. Now we can also find the phase difference from a displacement against time graph. Now the separation between the 2 points will now be in units of time. So if that's t, then the phase difference is going to be a fraction of a full cycle, so it's going to be t divided by capital T, where capital T is actually just the time period. If we're in degrees, the phase difference is going to be t over capital T times 360. If we're in radians, it's going to be t over the time period, multiply this by 2 pi. Let's cover transverse and longitudinal waves. So a transverse wave is a wave where the oscillations are perpendicular to the direction of energy transfer. Whereas in a longitudinal wave, the oscillations are parallel to the direction of energy transfer. This also leads to compressions and rarefactions. An example of transverse waves are EM or electromagnetic waves. It's important to note that all electromagnetic radiation travels at the same speed in a vacuum. This is given in the formula booklet, but the speed of light, typically given the symbol c, is right around 3.0 multiplied by 10 to the power of 8 meters per second. You can also have waves on a piece of string, for instance, as long as the oscillations are perpendicular to the direction of energy transfer, it's a transverse wave. You can also have longitudinal waves. An example of those, for instance, are sound waves. And now let's talk about polarization. What is the definition of a plane polarized wave? So the oscillations of the particles or the fields are restricted onto a single plane. Because of that, only transverse waves can be polarized, because in a longitudinal wave, the oscillations are always parallel to the direction of motion anyways. Now, if you have a transverse wave, you can have a whole bunch of different planes through which you can oscillate. You can have a vertical plane polarization, in which essentially all of the individual particles are kind of going up or down like this, and that's going to correspond to this case. Sometimes you will see in textbooks and exam questions this symbol for a vertical plane polarization. You can also have a horizontally plane polarized wave. In this case, the particles are going to be moving horizontally like so, along this line, and so on and so forth. You can also have a mixture of these in which the wave is oscillating along all planes, or has a component of polarization in the vertical plane, a component in the horizontal plane, and if that's the case, you have unpolarized wave. The symbol that you will sometimes see is this one here, signifying that it has a vertical component and a horizontal component. Just as a side note, but very often sunlight is an example of an unpolarized wave. In particular, non-reflected sunlight. We're about to go into this in a little bit more detail. And now let's have a look at an application of polarization, namely Polaroid materials. But first, let's take a moment to appreciate my drawing. So this drawing is definitely not up to scale, by the way. We have some sunlight which is being emitted from the sun in all directions. Initially, this light is unpolarized. And then that light, let's say it travels to the surface, it strikes the surface, but then after it is reflected, most of the light is horizontally polarized. So only this component is left. Maybe we have like a tiny vertical component, and this reflection over here, which is mostly horizontal, I know I'm exaggerating it, this is what reaches our Polaroid. However, our Polaroid only transmits the vertical component of the light. The horizontal component is absorbed. That means that most of the reflected light will actually be absorbed. So most of the reflections will be absorbed by the Polaroid, and that's going to reduce glare and reflections. If there are other things around here, I don't know, let's say that there's a piece of rock or something like that. I know this looks like a square, but if there's something over here, then the light from it will not necessarily be horizontally polarized mostly, and we'll be able to see this with approximately only 50% drop in intensity, because only the component that is horizontal is going to be absorbed, and we still have quite a large vertical component. So to sum up, the Polaroids absorb the horizontal component of the polarization of light. Please note that in some questions you may be given a Polaroid that has been rotated, so the horizontal and vertical direction may change on the question, so please read the question really carefully. But in this case, it absorbs the horizontal component. The Polaroid transmits the vertical component. If light is unpolarized, 50% of the light will pass through the Polaroid. The reflected light is mostly horizontally polarized, so most of the reflected, this here should say light, will be absorbed, reducing the glare and the reflections. A different application of polarization is to be found in aerials for transmission and reception. Let's have a look at an example problem. We've got a transmitter of microwaves, there it is, and a receiver with an aerial which is shown. And we need to plan an experiment to determine if the transmitter emits waves which are polarized either in the vertical or the horizontal plane. So the first thing to note in this question is that we need some form of rotation. Typically, what we tend to be able to rotate is to rotate the aerial. We can start rotating it in one of the planes, for instance in the vertical plane. If the question specifically mentions the vertical plane in the question itself, we need to mention the vertical plane. If the aerial is vertical, when the signal shown on the receiver is at a maximum, the transmitter emits waves which have been polarized in the vertical plane. On the other hand, if the aerial is horizontal, basically this thing tilted on its side, when the signal shown on the receiver is a maximum, then the waves of the transmitter are polarized in the horizontal plane. And now let's talk about how a stationary wave is formed. An incident wave is reflected off a boundary or a fixed point. The incident and the reflected wave will then superpose, and places where the waves interfere constructively are known as antinodes. These are points of maximum amplitude. Places where the waves interfere destructively are known as nodes. And a node is simply a point of zero amplitude. What are the differences between progressive waves and stationary waves? Well, first of all, progressive waves actually transfer energy in the direction of travel, whereas in stationary wave, the energy is actually stored between the 2 points where the wave is. Additionally, in a progressive wave, the amplitude is constant across all points. Now, what do I mean by that? Imagine I have a rope between those 2 points and I send a progressive wave to travel. Then, let's say if the wave is going this way, each of those points is going to go up and down by the same amount, which is known as the amplitude. the amplitude itself varies on a stationary wave. So here is a stationary wave. Tell you what, let's just draw another one over here. So here is my stationary wave. Let's say we have something like this. Just to differentiate it further from a progressive wave, let's draw it like this. So if we're at this point, we'll constantly be going up and down like so with the maximum amplitude. Whereas if we're on a point right next to it, we are going to be going up and down with a slightly lower amplitude, and then slightly lower amplitude still, until we reach a node where we're going to have zero amplitude. So this here is 0, this here is a max, standing for maximum amplitude. And let's also talk about phase difference in stationary waves, which is a little bit tricky to understand. The two rules that I like to remember are that between adjacent nodes, all the particles are in phase, and particles on different sides of a node are in antiphase. Now, what does that mean? Imagine that we have a stationary wave. So let's say we draw a wave that looks something like this. This here is going to be a node, this here is going to be a node, and this here will be an antinode, node, so on and so forth. Our first rule says that between adjacent nodes, all the particles are in phase. Well, those are two nodes, and the particles between them are going to be in phase, meaning that all of those particles between the nodes are going to be going either up or down together like so. On the other hand, between those two adjacent nodes, all the particles are going to be going down. And this is where our second rule comes in place, and that is that particles on different sides of a node are in antiphase. So those two regions on the different sides of the same node are in antiphase. Just while we're talking about useful rules, the distance between adjacent nodes or adjacent antinodes is actually half of the wavelength. So for instance, let's say this distance between those two nodes, well, we can clearly see that this will be half a wavelength, and this one here will also be half a wavelength, but also between antinodes as well. So that will be this distance here. This will also be lambda over 2. By the wavelength, we mean the wavelength of the progressive wave which formed the stationary wave. The harmonics can be demonstrated by this lovely experiment in which we have a vibration generator. The vibration generator is typically, by the way, connected to something known as a signal generator as well, which can produce an electrical signal at a given frequency, and that moves the vibration generator at that particular frequency. We have a piece of string of a certain length between the pulley and the vibration generator, and then a mass underneath. We're going to notice that at certain frequencies, specific patterns appear. So the first harmonic occurs whenever the length is exactly equal to half of the wavelength. Well, how do we remember this? In this particular experiment, our wave is right between two fixed points, and those have to be nodes. Well, the first possible solution is actually just fitting in about, well, exactly half the wavelength. So L is equal to lambda over 2. One wavelength is the next possible solution, which means that between this node and node over a distance L, we can actually fit two half wavelengths. And in this case, L is equal to lambda. Notice that this is not a progressive wave, but a stationary wave. And then, of course, 3/2 lambda would be the third harmonic, each time adding in more half wavelengths. There's also something really important that will allow us to calculate any subsequent harmonics. So all the harmonics are multiples of the first harmonic. In this case here, I've just made up some numbers just for the sake of revision. Our first harmonic is, let's say, 30 Hertz. So if the first is 30 Hertz, then the second will be found at 2 times 30, which is equal to 60 Hertz. The third harmonic will be found at 3 times 30, which will be at 90 Hertz, and so on and so forth. And this is very often a very nice, easy shortcut to solve a question. Let's do an example problem. A stationary wave is set up on a string as shown below, and it's oscillated at the second harmonic. What we need to do is compare the motion of the following points. We have initially point 1 and then also point 3. The best way to tackle these questions is by identifying which are the nodes and which are the antinodes. So in the second harmonic, we have 2 half wavelengths. So this here will be a node, and this here will be a node. This here will be an antinode, and this here, point 2, will be an antinode. Now, notice that point 1 and point 3 are on the opposite sides of a node, and this means that there will be an antiphase. Please note that we can also say that they have a phase difference of pi radians or 180 degrees. Now, what if this question was, let's say, for 2 marks each? Another aspect that we can write is that all the points will have the same frequency. And if they have the same frequency, they will also have the same time period. If there was a grid behind this is just merely a sketch, we could probably compare the amplitudes as well. Now, tell you what, let's compare the amplitudes for part B, in which we need to compare the motion of points 1 and 2. Now, point 2 is the antinode, therefore point 2 will have the higher amplitude. Alternatively, we can say that point 1 will have a lower amplitude compared to point 2. And also those 2 points will also have exactly the same frequency, but also they will have the same phase. So we can say that points 1 and 2 are in phase. If we're ever asked to talk about the nodes, remember the nodes are actually stationary. They have 0 displacement, 0 amplitude. In the AQA formula booklet, you will find this equation that the frequency of the first harmonic only is given by 1/2L root of the tension in the string divided by the mass per unit length. Now, where does this equation actually come from? Even though the derivation is not actually on the spec, I find that it's pretty crucial to understanding and being able to apply this to new situations, which is what the exam is all about. So where does this come from? Well, if we have the first harmonic, notice how in the length L we can only have half a wavelength. You can think of this as 2 nodes, so this here from here to here is half a wavelength. Well, this here would mean that the wavelength will just be equal to 2L. But now remember that V, the wave speed, is equal to the frequency multiplied by the wavelength. This means that the wavelength will be equal to V over F. So we can plug this into here to get that V over F is actually just equal to 2L. Let's be consistent with our L's. We didn't have a capital L, so I'll just change that to a lowercase l. We're almost there. Now, shall we just flip this and rearrange for the frequency? So I'm going to do F over V is equal to 1 over 2L. Now let's carry on across here. F will be equal to 1 over 2L multiplied by the speed V. And now another equation that is sometimes given in the question itself is that V is equal to the square root of the tension divided by the mass per unit length. Okay, well, we can just sub this back into here and we are going to get that F is equal to 1 over 2L and then the speed is equal to T divided by the mass per unit length. Now, what do all of those symbols actually mean? So the tension is just equal to essentially the force which is acting on this piece of string. So let's say if we had a mass here M, then the tension will just simply be equal to mg. Mu here, which is the mass per unit length, and mu, which is the mass per unit length, the equation for that will just be equal to the mass of the string, which is divide that by the total length of the actual string. Now, something which I've noticed quite a lot is that sometimes you're given the density in the cross-sectional area of the cable or the actual string. So a really useful equation to keep in mind for mu, because this was equal to the mass of the string divided by the length of the string. So, but mass in general is equal to density times volume. So one thing that we can say is that this is equal to the density of the string or the cable multiplied by the volume divided by the length. But because our volume for a circular cable is just going to be equal to the cross-sectional area multiplied by the length, then this here will be equal to the density of the string multiplied by the cross-sectional area multiplied by the length. Divide that by the length. And notice how the two lengths are going to cancel. So this means that our mass per unit length will just be equal to the density of the string multiplied by its cross-sectional area. It's typically circular, but obviously do watch out what the question actually says. So this here will be given by pi d over 2 squared leading to the density of the string multiplied by pi d squared, divide that by 4. And this is something that I've seen quite a lot in AQA questions. We also need to go over a really important definition, and that is the definition of superposition. So when two waves interact, the resultant displacement is the vector sum of the individual displacements. The word displacement is typically underlined in mark schemes, meaning that we need to mention it to score full marks. But what does this definition actually mean? So let's say I have a point X and a wave arrives there, and as it's arriving, it's in this part of the cycle. Let's say that another wave arrives at that point at exactly the same time, and in this case their overall displacement is going to be equal to 0. When one is going up, the other one is going down, meaning that the overall motion is cancelled in a way. On the other hand, if we had two waves that were arriving in phase, so let's draw the other one, let's say a little bit smaller like this, then the resultant wave will have a displacement which will be the sum of this plus that, which is going to be something over here. So it's going to look something like this. roughly speaking, of course. Moving on to interference, we first need to consider a couple of really important terms. We're going to start off with path difference. Path difference is defined as the difference in path lengths between the waves that has been traveled that have been emitted by the sources. So what do I mean by that? Imagine that I have a couple of sources of waves. These could be speakers with sound waves, they could be two separate lasers, they could be two slits in the double slit experiment, etc. Now, if I pick a point P, and let's say that the point P is over here, then the distance traveled by source 1 to P is going to be this much. However, the distance traveled by source 2 to P will clearly be bigger, and that difference in distance will be the path length. We can even illustrate this by plugging in some numbers. Let's say that this distance from source 2 to P was, let's say, 7 meters. We would say that this here was 5 meters. Then in this case, the path difference would actually just be equal to 7 minus 5, which is equal to 2 meters. Please note that if we pick a point which is exactly between the two sources, the paths will be exactly equal because they're going to form this equilateral triangle like so. So we can say that if the point is between the sources, the path difference would simply be equal to 0, and this is simply because the waves from source 1 travel the same distance as they do from source 2. Very often, by the way, in AQA, we end up having to use Pythagoras to figure out some distances, so sometimes we may be given, let's say, this distance here, so just keep in mind that you may have to use the Pythagoras theorem at some point. Okay, now, what does coherence mean? So, two waves are defined to be coherent, and this is typically a 2 marker. The first and really important point is that they must have a constant phase difference, and the terminology is really important. The word constant is crucial. The other important aspect is that they need to have the same frequency, which is equivalent to saying that they have the same time period. Now, in practice, what does that mean? It means that the two waves do not overtake one another. So let's see if I can visualize this without an animation. So let's say that I have one wave which is like this, and then another wave which is in antiphase. Now, those two waves will have a phase difference of 180 degrees or pi radians. Now imagine we see this wave that has traveled to the right at some point into the future. Then I have to draw this quite carefully. Then the two waves will still be in antiphase. We didn't have a wave overtaking another wave. They still have a phase difference of pi radians. This can only happen, of course, if the two waves have the same time period / frequency, because otherwise they'll keep overtaking one another. So this here is an example of two coherent waves. If, for instance, we looked at it and then suddenly they were in phase, like so, then this here would be an example of non-coherence because their phase differences changed from pi to, let's say, 2 pi radians, etc. And now let's talk about Young's double slit experiment. So this here was one of the original experiments to prove the wave nature of light. So what we need to know for the exam is the use of two coherent sources or the use of a single source with double slits to produce an interference pattern. What I've drawn over here is the use of a single source with double slits to produce this interference pattern over here. What we actually have is a laser, which is essentially a monochromatic source. And if you remember, monochromatic simply means a source that consists only of a single wavelength. That's why lasers appear to be the same color as well, because the fluctuation wavelength is very, very small. So I've kind of drawn this pretty badly over here, but what actually happens is that you get diffraction. You get the wave spreading as it leaves each slit. And then those two sources end up overlapping, i.e. superposing, and places in which the waves meet peak to peak. So you can sort of imagine like a wave here and then a wave here. So at a maximum, the waves meet peak to peak, which means that they are in phase. On the other hand, if we have a minimum, for instance here, that's the interference pattern really. It's this continuation of these bright spots, which are maxima, and these dark spots, which are known as minima, and kind of intermediate intensity in between. But at a minima, the waves actually meet peak to trough. So if we were able to kind of zoom in, we would see something like this. The two waves essentially superposing and causing destructive interference. We can summarize this into the conditions for interference. The waves from the two sources must superpose. Maxima are caused by constructive interference, and for that the waves must be in phase. We can also say that the path difference is a multiple of the wavelength. Minima, on the other hand, are caused by destructive interference, and the condition for this is that the waves are in antiphase. And what path differences would actually work? Well, it actually has to be equal to a multiple of this expression, which is n plus a half multiplied by the wavelength. So for constructive interference, the path difference would simply need to be equal to a multiple of the wavelength, which is n lambda. But for destructive interference, we are going to need a multiple of half a wavelength, or one full wavelength plus half a wavelength. So we're going to need n plus a half lambda, where n is an integer in both of these expressions. Calculations in these types of questions typically involve the famous Young's double slit equation. Now, in this equation, W is the fringe separation, which is the distance between the center of a maximum to the center of another maximum. Please note that if you're doing a paper 3 question, what you should really do is measure multiple of these, for instance 10 of them or so, and divide that number by 10 to reduce the percentage uncertainty. Lambda is the wavelength of light. The distance d is the distance from the slits to the screen, and s is the slit spacing. This here is usually measured with a traveling microscope, if that ever appears on a question. And now let's go through a proof of Young's double slit equation. So let's pick a point on the screen that will end up being a maximum. So let's just pick this point. The path difference, or the path from one of these slits, let's go from the middle of the slit, is going to be approximately this one over here. On the other hand, the path to the other slit will be just a little bit bigger. Let's just draw that over here. We can find the path difference, which is simply going to be just this distance over here, which will end up having a 90-degree triangle like so. So the key bit about this proof is that our distance to the screen D has to be significantly bigger than the slit separation S. I've only drawn this relatively big simply so that we can visualize this a little bit better. Let's just say that this here is the central maximum and this here is, let's say, the first maxima that we can see after the central maxima. Okay, so the path difference in this case should be exactly equal to the wavelength. And the two rays, in a way, are going to differ by this distance over here. Now, let's pick one of the angles. So I'm going to call this angle theta. I can say that the sine of the angle, sine of theta, which will be equal to the opposite divided by the hypotenuse. Now, my opposite in this case is simply the wavelength, which is the path difference for the first fringe. Divide that by the hypotenuse, which in this case is just the slit spacing. Because this triangle is actually really stretched out in the limit that d is significantly bigger than the slit separation, then we can say that sine of theta is approximately equal to theta. So therefore we can say that theta is approximately equal to lambda over s. Now, what we want to do as well is have a look at the 2 points across here. So this here was the central maximum. Let's call that point 1 and point 2, and the distance between them is actually W. Let's just be a little bit more precise. We can actually invoke them into another triangle because this distance D here will have a 90 degrees to the screen, and meaning that those two triangles will actually be just similar. So if I was to make this triangle like this, I mean this one right over here. Well, because of that similarity, this angle here is also theta. So by looking at this second triangle, we can say that tan of theta, which is approximately equal to theta, is then going to be equal to the opposite divided by the adjacent, which is W divided by D. So this means that lambda over S is equal to W over D in the limit that the distance D is significantly larger than the slit separation. Just rearranging for W, we get that W is going to be equal to lambda D divided by S. And here's a really important example question. We have a microwave transmitter and those are picked up by a microwave receiver. Some of the microwaves will go in this path, which is the direct path. Others are going to go up and they will be reflected by this aluminium reflective plate, and then they will also end up back at the receiver. Imagine that we take this aluminium plate and we simply move it upwards. What will happen to the signal picked up at the receiver? The first thing to note is that there will be interference because the reflected and the direct microwaves will end up superposing. Then a really useful tip would be to comment on the two PDs. Path difference and also potential difference. Sometimes in these questions we may even need to do a calculation for the path difference, but in this case we just need to explain it. So what we're going to say is that as the plate goes up, the path difference increases, which also means that the phase difference will be continuously changing. The signal itself will fluctuate between maxima and minima. This signal typically is actually the reading of a sensitive ammeter that's connected to the actual receiver. I'm just going to carry on up here because I'm running out of space. Whenever there is a maximum, the path difference will be a multiple of the wavelength. And whenever there is a minimum reading, the path difference will be equal to n plus a half multiplied by the wavelength. Let's do another one of these because these questions are just so incredibly important. We have two speakers that produce sound waves. And then we have a student that finds a maximum intensity using a microphone connected to an oscilloscope at a certain point P. What we need to do is explain the conditions for a maximum. The first thing that we need to say is that the waves at point P, the waves need to superpose or interfere. Now, in order for there to be a maximum, we need to comment on the two PDs. Let's start off with path difference. We could even write down an equation for it, and we can say that path difference, I'm going to write PD for now, is equal to n lambda. The other PD that we need to comment on is the phase difference. So the waves from both speakers need to arrive at P in phase. So what does in phase means? A phase difference of 0. Well, in this case, it's not going to be 0 because it's not exactly right at the center, but it could be 0 if P was right at the center. But this is just an explanation in brackets, so that'll be 0, 360, 720, etc. So that's n multiplied by 360, where n is just an integer. And now we're going to do exactly the same question. However, I've changed the word maximum to a minimum. So imagine the reading at P was a minimum. What are the conditions for minimum intensity? Well, the waves also need to superpose to produce a minimum. But now we have a different equation. The path difference needs to be half a wavelength plus another wavelength or plus two wavelengths, etc. So multiples of these. So the path difference will be equal to n plus a half multiplied by the wavelength. And finally, the waves from both speakers need to be in antiphase. So for instance, this could be 180 degrees out of phase or pi radians. And let's do one more example. So we have the same diagram, however now it is definitely not drawn to scale, and we can assume that the distance to the microphone D is significantly larger than the separation of the speakers. So a student moves the microphone along the vertical line PQ and finds the separation between maximum readings to be 0.45. Explain what will happen to the distance between adjacent maxima if the separation between the centers of the speakers is halved. Okay, so we can definitely use our fringe spacing equation. Our fringes in this case are going to be the maxima. So we know that W will be equal to lambda D divided by S. So assuming that the wavelength is constant, we can say that the spacing between the fringes, in other words, the spacing between the maxima, will double, because if we were to halve this, we are decreasing it by a factor of 2, and if lambda and D are constant, W will increase. So we can say that this is because W is inversely proportional to the separation of the speakers. And we have also assumed that the wavelength is constant. The final bit that I'm just going to probably write over here is to actually give a value. Because we are given a value in the actual question, we can say that the new W, or the new separation between two readings, will be 2 times 0.45, which is going to be 0.90 meters. There's also a spec point that sometimes makes an appearance in exams, and that is the production of interference patterns using white light. So if we end up using white light in the double slit experiment, what we are actually going to get is all the colors on the actual screen. Why is that? Well, because the different colors are going to have different wavelengths, they're also going to have different fringe separations. So the fringe separation is the distance, let's say, from a max to a max, or from a max and a min. Now, everything else will be the same. However, because the fringe separation is equal to lambda d over s, so if d and s are constant, the longer the wavelength, well, the higher the fringe separation, because they are directly proportional. Let's try and draw it maybe. So blue is going to have a very short wavelength, so we're going to get some sort of a blue spot. Let's say the next blue spot is over here. Let's say that green is something in between. So the central one will be here, but then the next one will just be a little bit longer, somewhere over here. Red will also be sort of here, and then the next one will be sort of over there. Now, the combination of all of those arriving at the central maxima will make a central max which appears white, but then all of the other colors are going to spread out, with blue/violet the closest. That has the lowest W, and this is simply because blue has the lowest wavelength, whereas red has the highest wavelength, so it will have the greatest separation. Hopefully that makes sense. And now let's talk about diffraction. First of all, what is diffraction? Well, it's the spreading of light as it passes through a gap or around an obstacle. The condition for diffraction is relatively simple. The gap size has to be approximately equal to the wavelength. In other words, this distance here, I don't know, should we just say that the gap size, I'm just going to call it A, has to be approximately equal to lambda, at least of the same order for maximum diffraction. Our next point from the specification is the diffraction pattern from a single slit with monochromatic light. Remember, monochromatic light simply means light source that produces just individual single wavelengths, which tend to translate to just one color. For instance, red is quite commonly used in the lab due to safety. As the source passes through the gap, it spreads out, and then it's going to create a wide central maximum with narrower side fringes. And we need to remember the explanation of this pattern. Remember, there's only 2 points really that we need to remember for the exam. It has a wide central maximum, which is kind of like I've tried to show that over here, and then narrower side fringes on the side. But what if we used just white light to produce a diffraction pattern? So if we have some incident white light, and here is the gap, the wave will still spread out. However, not at the central maximum. So all the wavelengths are going to arrive together at the central maximum, so the central spot will appear white. At all the other orders though, I've only drawn the first order here, we're essentially going to get a little rainbow. The colors are going to separate, and each wavelength is going to spread with a different angle from the gap. Red is going to have the largest angle, and it's going to be right at the top. Blue/violet is going to have the smallest angle, and hence it will be down here. Important to know that this is just the first order of diffraction, and this whole rainbow pattern would repeat sort of, let's say, over here, and then over here as well, for however many orders we can actually see. There's also a really specific specification point, which is the variation of the width of the central diffraction maximum, essentially how wide this thing here is. Should we just call that W, compared to the wavelength, and also the width of the slit, should we just call that S. So what we need to remember for the exam is that increasing the wavelength increases the width of the central maximum. Increasing the slit width, on the other hand, decreases the width of the central maximum. This is for qualitative treatment only. We don't really need to remember any equations. I personally find it quite useful just to remember that the width of the central maximum is proportional to lambda divided by s, assuming everything else is constant. For instance, the distance to the screen, typically given the capital D letter, is constant. What you would typically use in class, though, is a diffraction grating. Now, what is a diffraction grating? So it looks like this, and there's multiple different openings. This is not drawn up to scale. You can't actually see the openings with your eyes because there's many of them over a very small distance. A very typical diffraction grating might have something of the order of 300 lines per millimeter. What you will then see are distinct dots producing what is known as a diffraction pattern. The equation that governs this is the famous diffraction grating equation d sine theta is equal to n lambda. First of all, we're going to explain the symbols, then we're going to do a small example problem, and finally we're going to derive the equation as well. D in this case is the line separation. I often like to remember that D is equal to 1 over n, where n is the number of lines per meter. We need to be really careful with the units in this. Why is that? Because n being the number of lines per meter, not per millimeter. Typically in the question and in diffraction grating, we're given the lines per millimeter, so we need to convert that. 300 lines per millimeter is actually going to equate to 300,000 lines per meter. Now, what do the other symbols in the equation actually mean? The sine of the angle is the angle corresponding to the order of diffraction. In other words, this integer n. So for n is equal to 0, the beam just goes straight through, or part of the beam just goes straight through with an angle of 0. For n is equal to 1, it's going to have its corresponding angle, theta 1. This angle is going to be the angle between the diffraction grating and the first fringe. Because the pattern is fully symmetric, this will be 100% equal to the angle here, which is also going to be theta 1. Theta 2, the angle will be the corresponding angle between the diffraction grating and n is equal to 2, so that's the angle. Let's use a different color, like so. This one here is theta 2. Correspondingly, this angle here will also be equal to theta 2. Now let's just showcase how this equation works. Shall we say that theta 1 is equal to 10 degrees. So d sine theta is 1 over n sine of the angle, and this will be equal to just lambda, for n is just equal to 1. So that's going to give us 1 over 300,000. So I'm going to add a factor of 10 to the 3, multiply by the sine of 10 degrees is going to be equal to the wavelength. So if we were to find the wavelength in this particular case, lambda will have to be equal to this expression. Plugging in some numbers into the calculator, we're going to get about 5.8 times 10 to the power of minus 7 meters. And here's a really important question on the maximum number of fringes. So we've got a laser light of a certain wavelength is used to produce a diffraction pattern. We're given the slit separation of the grating directly. What is the total number of fringes that can be observed? So in all cases, if we have some light heading into a diffraction grating, the angle between the fringes can at the very maximum be equal to 90 degrees. So we can say that d sine theta is going to be equal to n lambda. Then we can set theta to be equal to 90 degrees for a maximum. which means that d sine of 90, which is just 1, is going to be equal to n lambda. Now we can find the maximum order of diffraction, which is going to be given by d over lambda. Now in this case, d is directly given rather than the number of lines per millimeter, so that makes our job a little bit easier. D is going to be directly 3.3 times 10 to the power of minus 6, and then we need to divide that by 640, multiply this by 10 to the power of minus 9. As a decimal, we're going to get around 5.16 or so, but we need to round this up to the closest whole number of completed integers. So in this case, n is just going to be equal to 5. But there is a trick. The trick here is that the total number of fringes. Okay, so what will the picture of this actually look like? We're going to have a central maximum here. That's going to be n is equal to 0. Then we're going to have 5 more spots above it. But that's just one side of the symmetric pattern. We're also going to have 5 more spots. That's going to give us a grand total of maximum number of fringes to be 11. And this is really, really important. As a rule of thumb, unless there's something that's obstructing it, we're always going to have this to be an odd number, which because we're going to have the same number on both sides plus the central maximum. So it could be a useful technique for multiple choice questions in particular. And let's go over the derivation of d sine theta is equal to n lambda. So imagine that I have a diffraction grating, and this here are just 2 slits, and the distance between them is just d. If p is the first order diffraction maxima, in other words, n is equal to 1, and right over here we're going to have the central maximum, n is equal to 0. So the first step in this derivation is to consider the path difference. So those two paths are going to differ by this distance here. If the angle to the first fringe is theta, the yellow triangle right over here is typically assumed to be similar to this one over here, which I believe is actually a tiny approximation, but this is typically true because the slit separation is significantly smaller than the distance to the actual screen. So we can say that the blue triangle essentially is similar to this yellow triangle. And if those triangles are similar, then this angle here will just be theta. And now we have this triangle in which we're going to have 90 degrees here, d, and then theta. Well, because sine of theta is equal to the opposite divided by the hypotenuse, and our opposite in this case is actually just the path difference. So in this case, sine of theta will just be equal to the path difference over the hypotenuse, which is just d, meaning that our path difference will just be equal to d multiplied by sine theta. But because the waves arrive in phase at p for constructive interference, the path difference is just going to be equal to n lambda. This is just a condition for constructive interference, and there we have it, that n lambda is equal to d sine of theta. We also need to talk about safety issues associated with using lasers. Some common sense applies here. Do not shine the laser towards people. Do not shine it on reflective surfaces. And also it's quite useful to have a warning sign displayed to warn people that you're actually using a laser. Sometimes in questions you also get 1 or 2 markers on the application of diffraction gratings. So there's multiple different ones. A couple of obvious ones is that they're used in atomic spectra to identify elements in stars in astronomy, also on Earth as well. But X-ray diffraction is used to study the structure of crystals in X-ray crystallography. This is very, very interesting. It's because the X-ray's wavelength is of similar order to the spacing between the atoms. So the atomic lattice itself is going to act like a diffraction grating. And now let's talk about refraction. The refractive index is defined as the ratio of the speed of light in a vacuum to the speed of light in a substance. We have this classic formula that n, which is the refractive index, is equal to c, which is the speed of light in a vacuum, 3.0 times 10 to the power of 8 meters per second, divided by the speed of light in that particular substance. It is important to note that the refractive index is actually unitless. Why is that? Well, if we consider the units of C, those are just meters per second divided by meters per second. They're just going to cancel out, leading us to the fact that N is unitless. Please also note that because nothing can exceed the speed of light, N has to be greater or equal to 1. So for air, we actually have a very tiny refractive index, like 1.006 or something like that, but it's approximately equal to 1. This is approximately equal to N in a vacuum, and we just assume that to be equal to 1. And here's a really popular style of question. So the refractive index of the glass shown is 1.5. What is the speed of light in this glass? Well, N is equal to C over CS, meaning that we can just rearrange for CS, which is going to be C over N. So that's going to be the speed of light in a vacuum, which is 3.0 times 10 to the power of 8. Divide that by N, which is 1.5. Well, this here is just going to give me 2.0 times 10 to the 8 meters per second. Now, how can that be? Remember that V is equal to F multiplied by lambda. So if the speed was to change, should we even call that CS just to be absolutely consistent? But if the speed is to change, then either the frequency or the wavelength must change. It's really important to note that the frequency always remains constant during refraction. It is the wavelength that changes and also the speed that actually changes. Let's also revise some rules about refraction. If I have a beam which enters at 90 degrees, let's draw it over here, then it's going to enter at 90 degrees, but it also is going to travel through, it's going to leave at 90 degrees. If I have a beam which arrives at an angle, so let's draw this one over here. The first thing to do is to draw the normal, which is going to be around here somewhere. Let's say that here is the normal. So if we're going to a high refractive index, the beam will reflect towards the normal. So the beam itself would have changed direction. This one here is the angle of incidence. It's always the angle to the normal. Let's call it θ1. And this one here is the angle of refraction. Let's call it θ2. Then on the other hand, at the second boundary, we're going from a higher refractive index to a lower refractive index. Well, if that's the case, the beam will bend away from the normal. So it's going to do something like this. Something to note is that this line here ends up actually being parallel to this line here due to pure geometry. And sometimes this is asked in questions as well. But what will this angle of refraction actually be exactly? Well, this can be determined by Snell's law of refraction for a boundary. This says that the initial refractive index, let's call it N1, multiplied by sine of θ1, being the angle of incidence, is going to be equal to N2, which is the refractive index of the second substance, multiplied by the sine of the angle of refraction, θ2. And this is often applied to lots of problems. Let's talk about total internal reflection. Imagine that situation that we had before. We had a glass block, and then we're going from glass, n is equal to 1.5, to air, n is equal to 1. We can go down a few different paths. For instance, if we go down this path, then we're going to emerge a little bit away from the normal and towards the boundary. If we take this path along here, we're going to get a little bit further away from the normal and a little bit closer to the boundary. But if we take a special path, which is going to correspond to this special angle to the normal, then we're going to emerge exactly parallel to the boundary. And this angle of incidence is known as the critical angle. And above this angle, only pure reflection occurs rather than any refraction. If we're going to go above that critical angle, we are going to remain perfectly inside, totally internally reflected inside of the original substance. And this is known as total internal reflection. How do we derive this angle? Well, let's use Snell's law. So I'm going to write that N1 sine theta 1 is equal to N2 sine of theta 2. I'm going to call the angle of incidence at which total internal reflection occurs to be the critical angle. And this happens when theta 2 is equal to 90 degrees. And then we get that N1 sine of theta critical is equal to N2 sine of 90 degrees. But remember, sine of 90 is just 1, therefore we get that N1 sine theta critical is equal to N2. In other words, sine of theta critical will just be equal to N2 divided by N1. And this is a formula given in your formula sheet. Remember, in order for this to mathematically work as well, sine of the angle has to be smaller than 1. It's sandwiched between 1 and minus 1. Therefore, this only works if N1 has to be bigger than N2. So it's going to work on the boundary going from, let's say, glass to air, but it's not going to work the other way around. And let's also talk about fiber optics, which are a fantastic way to transfer information. Here is the step index fiber optic. We have the core at the center, which is surrounded by cladding. The core actually propagates light waves by total internal reflection. The individual beam itself passes through the core, totally internally reflecting. We can sort of imagine it doing something like this. In order for us to have maximum transmission, the core needs to have low absorption. In exams, you may also come across the word attenuation, but that exactly just means absorption. The function of the cladding is twofold. It needs to protect the core from damage, but it also provides a boundary for total internal reflection because it has a lower refractive index compared to the core. Remember, this is actually the condition for total internal reflection to actually occur. There's several different problems. We have material dispersion, and that is that different wavelengths are going to have different speeds due to the different relative refractive indices in the core. For instance, red might have a very different speed to blue. One way of fixing this is by using a monochromatic beam of just one wavelength. You can also have modal dispersion where different paths have different lengths, so the effective time along the fiber differs. It can be used by using a single mode fiber which has a narrower core, smaller difference between the relative refractive indices of the core and the actual cladding. Sometimes this appears as delta N in the actual questions. Just a little note about the absorption of the core. It has a low absorption, but if it had a higher absorption, this would lead to a loss in the amplitude of the signal. And let's talk a little bit more in detail about modal dispersion. This is really caused by the light rays entering the fiber at different angles. So this actually leads to, what I should say, this leads to spreading of the pulses due to the pulses themselves taking different times to travel through the fiber. A different way of saying the same thing is that the pulses actually broaden due to entering the optical fiber at a different angle. The greatest transmission rate occurs when there is less modal dispersion. One way of achieving that is the smaller diameter, which means a smaller range of path, which means less broadening. Well done for revising the whole of waves. If you are revising for paper 1, have a look at this video which covers the whole of AQA particle physics. Click over here.